This is the review guide for the quarter 3 test. Number 1, the speed of sound is about 340 meters per second. It takes 5 seconds to hear an echo. How far away is the wall or cliff? We're going to use the velocity equation that we had at the first semester. 340 is the velocity of the sound. The time of travel is 5 seconds, and we're looking for the distance of the travel. So I'll multiply both sides here by 5, and I get 1,700 for the distance traveled. But remember, that distance is from the person to the wall or cliff and back to the person. We just want to know the distance from the person to the cliff. So it's half of the distance traveled by the sound. So you take half of 1,700 and you get 850. Number 2, a liquid has an index of refraction of 4. What's the speed of light in that liquid? So here's our index definition. C is the speed of light in a vacuum. That is always going to be 300 million. And then the V is the velocity in that material, in this liquid. So that stays a letter since that's what we're looking for. The 4 is the index. So we can put the 4 over 1 to make a proportion, and then you switch the diagonals. So we get V is 300 million divided by 4, which is 75 million. Number 3, a light ray travels at 100 million meters per second in a glass. What is the index of refraction for the glass? So we use the same equation, but this time we're looking for the N value. The C is still 300 million. It's always 300 million. The V is the velocity in the liquid, which the story problem tells us is 100 million. So 300 million divided by 100 million is going to be 3. Number 4, the energy of a light ray with a frequency of 4 million hertz. So capital E is energy. H is Planck's constant, which is 6.6 times 10 to the negative 34th. Frequency is 4 million. Multiply those together, we get 2.6 times 10 to the negative 27th joules. Number 5. Find the energy of a light ray. Again, we're still looking for E, but this time we're given the wavelength instead of the frequency. So we have a slightly different equation. H is still Planck's constant. V is the velocity of light in the story problem, which we're told that it's in a vacuum. So the velocity of light is always 300 million in a vacuum. And the wavelength we need to have in meters. 5 millimeters is 0.005. So do all that math and you'll get 3.96 times 10 to the negative 23rd. A ray goes from air to crystal. The ray hits a crystal at an angle of 43 degrees to the normal, 47 degrees to the surface. What is the angle of refraction? So we're going to be using Snell's law here. N1 is the index of refraction for the first material that the ray is in, which we're told here that's from the air, so that's the first material. N is 1. There's our 1 there. The angle is the angle in the first material, and we're given 2 angles here. One is 43 degrees, one's 47. We use the angle that is between the ray and the normal, 43. We do not use the angle to the surface. That's bad. That's just there to confuse you. Okay, so the theta is 43. The index of refraction of the second material is 2. And we're looking for the angle on the inside, the angle of refraction. Okay, do all this math, then you'll get 19.8. Remember, you're going to have to first turn the sign of 43 into a decimal, divide by 2, write down that number, and then take the inverse sign of that decimal, and you'll get 19.8 degrees. Number 7. A ray goes from air to an unknown liquid. The ray hits the liquid at an angle of incidence of 20 inside liquid. The angle of refraction is 10 degrees. What is the index of refraction for the liquid? So we're looking for the N value. Here's Snell's law, and we're looking for the N in the second material, the liquid that it's in the second place. So air is our first location, so the N is 1. We're told the index of incidence, the angle of incidence is 20. And we're told the angle of refraction is 10. So sine of 20 we can change to a decimal, 0.34. Sine of 10 we can change to a decimal, 0.17. Divide both sides by 0.17 and you get 2 for the index of refraction. Number 9. Draw a ray diagram to draw the image of the object. The mirror is concave like the inside of a bowl. The focal length is 10. The object is 30 in front of the mirror. Then use the equation to find the distance. So here's the ray diagram. We're reflecting on the inside of the bowl. There's the focal length at 10. The image is much farther away. Oh, the focal length is 10. The object is much farther away at 30. So if you draw the first ray parallel, it reflects through the focal point. The second ray goes through the focal point and reflects parallel. They crisscross right there. That's the image. It's very small. It's underneath the main axis, and so it's upside down. It is a real image because the light rays really do travel there. It is between the focal point and the center of curvature. So it's somewhere between 10 and 20 centimeters from the mirror. To find the exact location, we're going to be using the Fedoti equation. F is the focal point, 1 over 10. DO is the object distance, and that's 30, so we have 1 over 30. We're looking for the image distance, DI, so that stays a letter. Change things into a decimal, 0.1, 0.033. Move the 0.033 to the other side, subtract it from both sides, we get 0.067. And that is equal to 1 over di, 1 over di, 1 over di. But we don't want 1 over di, we just want plain old di, so we got to flip that over. And if we flip one side, we got to flip the other, so that goes underneath. 1 divided by 0.067 is 15. Number 10, draw a ray diagram to draw the image of the object. The mirror is concave like the inside of a bowl. The focal length is 40. The object is 20 in front of the mirror. Use equations to find the image distance. So here's the general ray diagram. We have the focal length at 40 and the object is much closer at only 20. So the first ray I draw is parallel to the axis and it reflects through the focal point. That's the same thing as up here. The second ray, though, is different. It comes from the direction of the focal point, hits the mirror, and bounces parallel. These two rays appear to have come from that spot right there. And so the image is much taller than the object. It's magnified. It is behind the mirror, where the light rays only appear to have come from. They don't actually pass behind the mirror, so this is a virtual image. And it's right side up. To find the exact location, we use Fedoti. And I'm going to use a different sheet of paper here for that. We have 1 over the focal length is 1 over 40. 1 over the object distance is 1 over 20. 1 over the image distance is still the variable. Change things into a decimal. 1 over 40 is 0.025. 1 over 20 is 0.05. Subtract off 0.05 from both sides, we get negative 0.025 equals our reciprocal. So we got to flip this, flip the other side as well, and we get the answer of negative 40 centimeters. So that's behind the mirror. Okay, next, draw a ray diagram to show the image of the object. The mirror is convex like the outside of a bowl. The focal length is 10. The object distance is 5. Okay, I have here a note saying it's the same diagram as number 10, but that's not quite right. I just recognize now that this is like the outside of a bowl, whereas the previous one was like the inside of a bowl. So let's draw an image like that. So for number 11, it says that the focal length is 10. And the object is 5. And this is like the outside of a bowl, so I have to draw it this way. There we got it. Okay, the first ray is going to be parallel to the axis, and it reflects from the focal, as if it came from the focal point, which is way back over here. So it's going to bounce upwards like this. The second ray is going to go towards the focal point, downwards at an angle, going towards us, but it's going to reflect parallel. so these two rays appear to have come from a spot right here, and so the image is reduced, it's upright, and it's virtual. Okay, so putting in our numbers now. 1 over f is going to be 1 over negative 10, so it's going to be negative 0.1. The object distance is 5 centimeters, and that's on the positive side, so it's 1 over positive 5, positive 0.2. That equals 1 over do. Subtract off 0.2 from both sides, and we're going to get negative 0.3. That equals 1 over di. And 1 over 0.3, I think that's going to be 33333. Let's make sure. 1 divided by 0.3 equals, sure enough, 3.333. So I got to change this. 3.33. It is still negative, though. With this kind of a mirror, both the focal point and the image will always be in negative values. Okay, draw a ray diagram to show the image of the object. The lens is a double convex football shaped. The focal length is 10 centimeters. It's 30 centimeters from the lens. Okay, I have here that it's the same as number 9, but that's not quite right. In number 9 we have a mirror. Here we have a lens. So I have to scribble out this note here, and we got to do it all ourselves. So here's our football shaped lens. We have focal points on both sides, and they are 10 centimeters. And then we have the object is 30 centimeters away. That's much farther, so I'm going to squeeze it in over there. That's not quite proportional, but it's the idea that we're farther away from the focal point. Okay, so the first line is going to be parallel to the axis and then through the focal point. The second one is going to be through the first focal point, and then it's going to be parallel. And so we'll have the image right there. Okay, let's use the Fedoti equation to figure out exactly where this is. 1 over f equals 1 over do plus 1 over di. 1 over f is going to be 1 over 10. 1 over do is going to be 1 over 30. And then we have our di is still a variable. This will be 0.1. This will be 0.033. Subtract off 0.033 from both sides, we get 0.067 is 1 over di, and so that means then that di is the reciprocal of 0.067, and if I remember correctly, that's going to be 15. Yep, 14.9. And that's our answer for that. I'm going to stop here, and you'll see other questions on another video.